Okay, so we're going to shift gears from graphs, and we'll go down to chapter 6, which is a little bit about counting and probability. So counting is harder than you'd think, right? It's not just 1, 2, 3, 4, 5, 6. There are 4 major concepts that we want to think about in counting: multiplication principle, addition principle, inclusion exclusion principle, and complements. So the multiplication principle, the number of options at each step get multiplied together to find the total number of outcomes. Formally, if you have n, capital N steps, and n sub I choices at the ith step, the total number of ways to do the activity is the product n1 times n2 times ... times n sub capital N. The addition principle, the inclusion exclusion principle, and the complement principle all come off the same idea. But they're about counting things in sets, and we just have to be careful about sets overlapping. So a definition and some notation: if S is a finite set, absolute value bars around S is the cardinality or the number of things in the set. And so the addition principle is this: if 2 sets don't overlap, the number of things in both sets is the sum of the number of things in each set. So if A and B are disjoint, right, no intersection, then the union of the two, which is putting the 2 sets together, the number of things in the union is the number of things in A plus the number of things in B. So the inclusion and exclusion principle is this, is because if they do overlap, how many things are in S and T if they do overlap? Well, when we take the union of S and T and we want to know how many things are in that, well, I say everything in S, everything in T, but everything that's in both S and T gets counted here and gets counted there. So we want to subtract off the intersection because otherwise things will be double counted. And in some problems, we'll get addition and multiplication principles mixed together. A very useful aspect of the addition principle is corollaries. So U is the universe set. That's whatever, for whatever problem you're doing. A is some subset. The union of A and A complement, remember that A bar complement A. Well, A and A bar together make up the entire universe set U. And so the universe set can be split into 2 parts: everything in A, everything in A bar, the complement of A. So here's a couple of examples of starting with the multiplication principle. So we have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you want to make strings of 5 symbols. How many possibilities can you make? Well, 1, 2, 3, 4, 5. Your first thing, your second thing, your third thing, your fourth thing, your fifth thing. Pick one of these to be the first one. There's 10 possibilities. Pick one of these to be the second one. There's 10 possibilities. Pick one of these to be the third one. Pick one of these to be the fourth one of those to be the fifth one. So that's 10 to the fifth, which is 1, 1, 2, 3, 4, 5, 100,000. Not particularly surprising, right? How many numbers are there between 0 and 100,000? Well, 100,000. Well, between 0 and 99,999. Note that we did not say you could not repeat symbols, right? So I get 10 options for the first, but I also get 10 options for the second. I can repeat the symbols there because there was no restriction there. This one is saying how many have no repeated symbols. So I would have 10 options for the first. If I used one and I can't repeat them, then I would only have 9 for the second, 8 for the third, 7, 6. And if you multiply all that out, you get 30,240. That's how many repeated symbols, how many strings have no repeated symbols. Okay. How many strings have repeated symbols? Here's where complements come in. We have 100,000. How many strings have repeats? That was 30,240. Every string either has a repeat or not repeat. These are complements. You have 100,000 total strings. These are the ones with repeats. What are the numbers without repeats? Well, it's 100,000 minus that, which is 69,760. Most of the strings don't have repeats, but some of them do. Right, and so there's the power of using complements. You can figure out how many have repeated symbols by finding out how many have not repeated symbols, which is pretty easy, and then subtraction. So how many strings with no repeats start with 871? So we're talking about strings of 5 letters. If you start with 5 numbers, if you start with 871, you only have 2 spaces left. You have 10 choices here, and you have 9 choices there. Oh, no repeats, sorry. So you've already got 3, so you only have 7 choices here and then 6 choices there. So 42 choices, because you have 7 choices for the 4th letter and 4th digit and 6 choices for the 5th, so 42. So how many strings with no repeats have the sequence 871 in there somewhere? This gives me cases. There's 3 separate cases. We could start with 871, or we could have the 871 in the middle, or we could have 871 at the bottom. And so this is the addition principle, because we have 3 things that don't overlap, right? And we just add up the number of things in both sets. So the addition principle, if you have cases, right, you generally use addition. So there's 42 of these, there's 42 of these, there's 42 of these. It's 126 total strings have 871 in them somewhere. So how many strings with no repeats do not have the sequence 871 at all? Well, again, this is complement. So there's 126, have 871 in this somewhere. There's 30,240 strings with, I got these backwards. This was no repeats. That's repeats. Sorry about that. There's 30,240 that have no repeats. So 30,240 strings with no repeats minus the 126 that do have the sequence 871. That gives me 30,114 that have no repeats and do not have the sequence 871 in them at all. Oof. So 132, how many strings with no repeats have the sequence 132? Same analysis here, just replace the 871s with 132. There's 126 total. So how many strings with no repeats have both the string 871 and the string 132? Think about it in a minute or two. The only way you can have both, since you're only allowed to use 5 digits, is to have the string 87132. Right? That's got 871 in it. It's got 132 in it. There's no other way to have both of them in there. So how many strings with no repeats have both the string 871 and 132? 871, there's 126. 132, there's 126. This string is counted once here and once there, right? Because it's got both. So the total with both would be 126 plus 126 minus the overlap, minus 1 occurrence of this string, because we don't want to double count it. So that's 252 minus 1, 251. Oh. So this is just 1. This argument was answering that question below. I got a little ahead of myself. How many strings with no repeats have either 871 or 132 or both? Well, there's 126 with 871. There's 126 with 132. There's one that's got both, but that gets double counted, so we need to subtract off 1 copy of that. And we're left with 251.